This is your presenter Asloob Mudassar, and I am presenting slide number 19 of the course on laser physics. Question: find the intensity of a laser beam at the focal plane of a convex lens with beam divergence equal to theta and beam diameter equal to capital D. Answer: the scheme depicted in figure 19.1 shows a diverging beam focused by a convex lens at its back focal plane. The size of the laser spot, as clear from the diagram, is D is equal to 2f into theta. If the lens is assumed lossless, the optical power at the focal plane will be equal to the power contained in the incident laser beam. So let me explain the diagram. Here on the left hand side we have the resonator output aperture. The beam is coming out from the aperture, and as well a diverging ray of the beam is also shown, making an angle theta with the optical axis of the beam, that is with the horizontal axis. Now at some distance I have placed a convex lens. The beam is incident on the convex lens, and you can see that the rays through the center of the lens have been shown, which on the focused laser spot meet at a plane perpendicular to that one located at the back focal plane, which is located at a distance f behind the lens. So you can see over here that I have shown the focused laser spot over there, and the diameter D, which is represented by small d, is equal to 2f into theta. So this is actually the diameter of the laser spot at its back focal plane. And in order to derive this result, you can consider a ray from the center of the lens, for example making an angle theta, going through the center of the lens and hitting the top point. So this is angle theta, and you can apply tan of theta, which will be equal to d by 2, because the half of the spot is the radius, which is equal to d by 2. So tan of theta is equal to d by 2 over f, and the tan of theta can be approximated as theta. So you can find that d by 2 is equal to f theta and d is equal to 2f into theta. So you can immediately work out this expression from this simple geometry. The caption of the figure is focusing of a diverging laser beam with the angle of divergence equal to theta. So we have found above that the size of the laser spot, as clear from the diagram, is d is equal to 2 into theta into f, shown in red. If we denote the optical power in the laser beam by capital P, then the peak intensity IP in the focal plane of the lens is given by IP is equal to optical power incident on the lens divided by the area of the spot. So this optical power P, which is incident on the lens, is the same as contained in the focused spot. So the power contained in the focused spot divided by the area of the spot, which is pi into d by 2 whole square. So the simplified result is 4p over pi into d square. And then we have represented d in terms of the previous equation, in terms of this expression, that is d is equal to 2f into theta. So making that substitution, we have the result ip is equal to 4p over pi into within the parenthesis, the square of the parenthesis contain 2p into theta, and then we have p over pi into f square separated, and then 1 over theta square separated from the expression. So on the right hand side of this one, which we regard as equation number 19.1, 1 over theta square from the equation 18.6 is 1 over theta square is equal to b, which is brightness, into the square of a pi d divided by 4p. So replacing the 1 over theta square with this expression on the right hand side of this one, the equation 19.1 reduces to IP, that is the peak intensity, is equal to pi over 4 multiplied by the square of d over f, and then the brightness b. And this is the equation number 19.2. For maximum light collection, the lens should be close to the resonator output aperture. For example, in this diagram, this lens should be close to this resonator aperture so that most of the light is collected by this lens. For maximum light collection, the lens should be close to the resonator output aperture, and the lens diameter dl may be considered equal to the size of the aperture capital D. That is, dl is equal to capital D, and the maximum intensity at the focal plane will be IP, which is the peak intensity, and max is the maximum value of the peak intensity, is equal to, within parentheses we have a pi over 4, and then the square of the parentheses contain dl over f, and then multiplied by capital B, the brightness of the beam. And this is equation number 19.3. So we have regarded this peak intensity as the maximum intensity because the lens is close to the aperture of the laser source, which means it will be able to collect all the whole power contained within the beam, and that power will be focused at the back focal plane of the lens, where we have regarded the peak intensity, and in this case the maximum peak intensity. This result can be expressed in terms of the numerical aperture NA of the lens, which is defined as, so numerical aperture of the lens is equal to refractive index of the air multiplied by the sine of phi, is equal to n air, that is the refractive index of air, is equal to 2 into 2 times sine of phi by 2, and is equal to n air into 2 into dl by 2 over f, because the sine of theta has been replaced by dl by 2 over f, because the dl by 2 is actually the half the diameter of the lens, and f is the back distance of the lens from its back focal plane, and phi is the angle formed at the center of the back focal plane. So from that one we have calculated sine of phi by 2, and we have multiplied by 2 because we have to contain the full width of the lens. So then we have a final result is equal to numerical aperture is equal to dl by f, which is shown on the right hand side of equation number 19.4, where phi is the angle formed at the focal point by the lens aperture. The equation 19.3 may therefore be written as, for example, this equation. So IP, that is the peak intensity, is equal to pi over 4 into square of numerical aperture multiplied by the brightness of the beam. For a given numerical aperture, the peak intensity in the focal plane of a lens is determined by the brightness of the beam. So if we have a lens which is fixed in numerical aperture or fixed in diameter and the focal length, which is dl over f, so if the numerical aperture is given or fixed for a lens, then of course the IP is determined by the brightness of the beam. As the laser brightness is very high in comparison with conventional sources, the same is also applicable to the peak intensity value. So it means that the peak intensity value at the back focal plane of the lens is also very high. This is the end of slide number 19.